Okay, welcome to the screencast video of Chemistry of Life, answering your muddiest points as collected. Quiz yourself here in this intro. What molecule is this food packaging from? Hopefully you got it. It's water. The first question that was asked was about atom versus molecule. So some definitions up here on the screen. You can read those. To keep in mind, when we have to draw an atom, the electrons go on the outside, they're negatively charged, and the protons, the positively charged particles, go on the inside. So electrons on the outside, protons on the outside, that's our atom. If you have more than one kind of atom bonded together, then you have a molecule. So here's an atom and a molecule, and this molecule happens to be water, where we see a hydrogen atom with one electron, one proton, another hydrogen atom over here with one electron, one proton, attached to an oxygen atom with all of its protons and electrons. So there are several types of bonds that will form between atoms or between molecules. One of the most important for biology is the covalent bond, which is a shared pair of electrons. If we have a structural formula of a molecule, like this water molecule structure drawn here, covalent bonds are always drawn as solid lines. Another way of looking at those bonds would be it's a shared pair of electrons. Here all of oxygen's electrons are drawn in red, hydrogen's electrons drawn in white. Now those hydrogen's electrons are spending more of their time kind of over by oxygen inside there, but they are shared. They continue to go around, and oxygen's electron is going around hydrogen. They're sharing this pair of electrons, and here this hydrogen atom is sharing this pair of electrons with oxygen. So rather than draw all these electrons moving around, we draw solid lines for a covalent bond, shared pair of electrons. When it comes to electrolysis, what we're doing is using an electrical current to break that covalent bond between the hydrogens and the oxygens. The equation for that we saw in the class was right here. Two water molecules reacting to produce two hydrogen molecules and one oxygen molecule. This is drawn kind of structurally here with hydrogen drawn in white and oxygen drawn in red to help you see how those pieces are being recombined. But basically with electrolysis, we're breaking the covalent bonds using an electrical current. Another question had to do with adhesion and cohesion and how they work together to form this capillary force. So defined here with an example, adhesion being the attraction of water molecules to another kind of molecule. So here's a water molecule attracted to some, looks like ammonia or something down there. With adhesion and cohesion, water molecules being attracted to themselves. And the attraction, to be specific with adhesion and cohesion, the attraction is a hydrogen bond. It's not as strong as a covalent bond. They're not sharing a pair of electrons, but it is a very weak attraction between the molecules of water to each other or water to something else. When that happens in a small tube, you get what's called a meniscus, where the water will pull itself up the sides. You have water molecules being attracted to this edge of the tube, that's the adhesion, and water molecules pulling on themselves, that's the cohesion, and together in a very small tube, the water will actually pull itself up. You can see it's pulled up this tube a certain distance, and if the tube gets narrower, it will pull up even higher. So the forces of adhesion and cohesion that act in water molecules are a direct result of water being polar. And there's a structural diagram of water drawn here, again with the electrons being shared between the hydrogen and oxygen. But those electrons spend more time with the oxygen than they do with the hydrogen, meaning that if something were to approach this hydrogen molecule from the side, it's going to appear slightly positive because its proton is exposed. Likewise here, approaching this hydrogen atom that's bonded to oxygen, it is slightly positive in appearance because its proton's more exposed. Approaching oxygen from above, it's got all kinds of electrons over here. If you recall, all these electrons that were inside of oxygen are hanging out, so it appears negative over there. So this makes water relatively negative on the oxygen side, relatively positive on the hydrogen side of it, and that's what we call polar. Now those positive ends will be attracted to the negative ends of other molecules. That attraction of the relatively positive side of one molecule to the relatively negative side of another molecule is called a hydrogen bond. Now compare that to a couple of other non-polar molecules that are shown here, carbon dioxide versus like gasoline. This is one of the molecules in gasoline, which is a mixture of things. This hexane gasoline molecule is completely surrounded by hydrogen atoms on the outside with all these covalent bonds, those solid lines inside to the carbon. This molecule is not going to have one side, top or bottom or left or right, that is more negative or more positive. So it doesn't have electrical poles. It's nonpolar. Same for carbon dioxide. It's also going to be nonpolar. Neither of these is going to dissolve as well inside of water because our solubility rules say that polar substances and nonpolar substances don't mix with each other. They say like dissolves like. Water dissolves polar molecules, not nonpolar molecules. That said, small amounts of carbon dioxide can dissolve in water, just not lots of carbon dioxide. One last note on solubility, to know that when you have a solution, we're saying that something is soluble in something else. The substance that's being dissolved is called the solute. The substance doing the dissolving, which in biology is almost always water, is called the solvent. So you have the solvent dissolving the solute, forming a solution. You'd say that the solute is soluble in the solvent. So those fancy terms. The concentration of a solution, the amount of solute inside the solvent, is another definition to know with solutions. Okay, our last question for Chapter 2 this week in the Muddiest Points discussion board was about energy charts, or I assume it means energy diagrams. Here we can see both options. Any chemical reaction is either going to release energy, so the products have less energy than the reactants, or it's going to absorb energy. The products have more energy than the reactants. In any energy diagram, energy is going to be drawn on the y-axis, going from a low amount to a high amount, and time, or reaction progress, goes from the past to the future. Reactants are always going to be on the left, products always on the right. We have this energy diagram. So there's only two choices. So just to keep in mind, either the products have more energy or less energy than the reactants. The other thing to keep in mind with both of these is that the highest energy on the chart is greater than both the energy of the reactants and the products. This line right here, and on this graph, it's this line that would be up here at the top. That energy is the activation energy. All chemical reactions require an energy in order to occur. If it's a really high energy, so from this reactant all the way up to this product, it's a lot of energy. That's a high activation energy. That reaction is going to happen slower or be more difficult to occur. If the amount of energy is less, so from these reactants to the activation energy is a less amount than compared to this one, this reaction would happen faster or be easier to occur. You can change the activation energy by either increasing the energy of the reactants, which would be easily done by heating them up, bringing the level up to a higher state, or using an enzyme, which is a molecule that would facilitate the connection of these reactants in a way that they could react to produce the products. So either enzymes are increasing the energy level of reactants. So you're warm-blooded and you have enzymes in your body, so you do both of those things to make your reactions happen faster. Okay, there are more, I thought, good questions related to this Muddiest Points. As the year goes on, my guess is going to be that these videos, I might even end up doing more than one video per chapter. Hope they're useful to you. Enjoy your studies.